Another phenomenon that didn't fit the simple wave theory for light was the phenomenon of line spectra. Now, before we describe what line spectra are, we need a couple definitions when we're talking about light. So light itself can be composed of monochromatic radiation. That means light that consists only of one single wavelength. Or most light that we're familiar with is actually polychromatic. So radiation or light that's composed of multiple wavelengths. And that's like the light from the sun, contains many, many, many different wavelengths. Now, if you take those wavelengths of light, all in one source of light, and split that light into all of its constituent wavelengths, such as taking a flashlight and shining it on a prism and separating those wavelengths of light out, then we produce what's known as a spectrum, where spectra is the plural of spectrum. Now, within spectrum or spectra, within spectra, there are multiple options. The light from the sun or from this flashlight here would produce a continuous spectrum, one that has no blank spots in it. It just goes from wavelength to wavelength to wavelength and so forth. However, if you were to take the light from a neon sign and run that through a prism to separate it into its constituent wavelengths, what we would observe is that we do not have a continuous spectrum. We have now a spectrum that has many blank spots and discrete lines of light, discrete wavelengths, with blank space all in between. And this is known as a line spectrum. Now, the existence of this line spectrum really made scientists look carefully at the atomic structure, because they said there must be reason. This light is coming from an excited neon atom. What's going on the atomic or even subatomic level that produces these very discrete wavelengths of light? And so they started with the simplest line spectrum that there is, which comes from hydrogen gas. So if you take hydrogen gas in a tube and run electricity through it, you will see this kind of purplish light come from the hydrogen. And that, if you split it into a line spectrum, shows only four discrete visible lines. There's a couple extra lines that are not in the visible region. We have four clear visible lines here. And so what they did is they looked at this and said, these lines appear at very specific wavelengths, and they proposed an equation that's known as the Rydberg Equation, which describes very accurately the positions of those lines. So the Rydberg Equation is simply the inverse of wavelength is equal to the Rydberg constant, which happens to be 1.097 times 10 to the 7th inverse meters, times, in parentheses, 1/4 minus 1/n squared, where n has to be a positive integer greater than 2. Now at this point, this equation simply describes where the lines appear. It doesn't predict anything. It doesn't have any physical meaning. And so it was in the very early 1900s that a scientist known as Niels Henrik David Bohr looked at the Rydberg equation and said, this must have a physical meaning. It fits the physical data very well. It must mean something on the atomic level. There must be something about the atomic structure that fits this type of an equation. So we remember back to Rutherford's model of the atom. This is from chapter 2. Rutherford had described the atom as containing the nucleus with protons and neutrons. And then all of the space around that was just where the electrons could be. There was no defined spots for the electrons, no confined spaces. The electrons could just be wherever around the nucleus. And Bohr looked at this and said, no, this makes more sense, or would fit the data better, if we propose a model where the nucleus is still at the center, but the electrons have very defined regions where they can exist. And he thought of those as being orbits. The electrons can orbit the nucleus, but it can only do so at certain distances away from the nucleus. And he then defined each of those orbits as being energy levels, where you could have an energy level, and he assigned to those energy levels a number. So a little bit more detail on this. Bohr defined n as being the principal quantum number, and just said that orbits can only exist at very discrete numbers of n, and that we can get the energy of those orbits from a simple equation, negative 13.6 electron volts times 1 over n squared, where n must be a positive integer value. And so then we can see that for n equals 1, we would be at negative 13.6 electron volts. And then as we move farther away from the nucleus, the energy becomes less and less negative. So we can think about it as becoming greater in energy as we move farther away from the nucleus. Now, he talked about this model of the atom for the purpose of describing the light that was given off by the line spectra, observed in the line spectra. And so what he said is that energy is absorbed or emitted as a photon of light when an electron changes orbits. So an electron can jump between these orbits, but to do so either requires energy or emits energy in the form of a photon. And he rewrote the Rydberg equation to describe the energy difference between these quantized energy levels as being the energy of the final energy level or orbit minus the energy of the initial orbit is equal to negative 13.6 electron volts times 1 over n final squared minus 1 over n initial squared. And in this case, the energy of a photon that is emitted is equal to the absolute value of the energy difference between those two orbits. Now, it has to be an absolute value because we certainly can't have a negative energy for light. And so from this equation, then, he could predict that if the change in energy is positive, if you're going from a lower value of n to a higher value of n, then in this case, a photon has been absorbed or energy has been put into the system in some form. We'll find out later that it doesn't always have to be a photon. We can put energy into the system in terms of heat. But then also if delta E is equal to a negative value, then that means that a photon has been emitted. We started out at a higher value of n and dropped down to a lower value of n. And so a photon is emitted to release that excess energy. Now, let's remember that the energy of a photon here, so this energy gap between the levels can be correlated to the energy of a photon and thus also correlated to the wavelength, according to the equation that Einstein used earlier. And so then using this formula that Bohr postulated here, he's now able to predict the hydrogen line spectrum, just like the Rydberg equation did, but now with physical significance. This is what n actually means. It's an energy level around the nucleus in Bohr's model of the atom. And he's able to find that this predicts the line spectra fairly well. So we'll do just a couple examples of this. So we'll say that we wanted to promote an electron from the n equals 1 to n equals 2 level. What energy would be required to do that? Well, in this case, we can simply use the equation, substitute 2 in for n final, 1 in for n initial, and we come out with the energy of the photon that would be required to do this would be 10.2 electron volts. Now, we were asked for the wavelength, so we first have to convert electron volts to joules, and then we can use it in the equation by Einstein earlier. So electron volts to joules, and then we rearrange E equals hc over lambda to solve for lambda, substitute values in, and come out with a wavelength of 183 nanometers. So this is deep into the ultraviolet region. If we wanted to promote an electron from the n equals 1 to n equals 2 energy level. But let's return back to the visible spectrum. Let's say that an electron was excited to the n equals 4 level of the Bohr model. What wavelength of light would be emitted if that electron dropped back down to the n equals 2 level? So we take the equation, n equals 2 is the final, n equals 4 is our initial. We come up with an energy of 2.55 electron volts. And then we can convert that, as we did before, to joules using that equation between electron volts and joules. We come out with the energy in joules, 4.085 times 10 to the minus 19 joules. Rearrange E equals hg over lambda to solve for lambda. Substitute everything in, and we come out with a value of 486 nanometers. This is in the visible region of the spectrum. What we can see, though, is that if we look at the hydrogen line spectrum, 483 nanometers is this kind of turquoise line right here. It's a good match. And if we compare just back to the Rydberg equation, we can see that when n equals 4, the Rydberg equation spits out 486 nanometers for this line spectrum. So this is the initial Bohr model describing the atom in an attempt to describe this physical phenomenon that was observed of line spectra.